Let's turn our attention to the so-called moment of a couple. After we're done with this lecture set, you'll be able to define what a couple is and determine the moment of that couple. There's lots of applications for this, and there are also, of course, example problems in the slides you need to go look at besides the examples that I worked for you. But basically what happens is if you have a set of forces in opposite directions, equal and opposites, let's say, at some distance, they will cause a moment. And being able to calculate the moment of a couple is, or a force couple, is important. It's something very useful to know because it actually occurs quite frequently. So applications, some straightforward applications of a force couple or things like turning a wheel, where you have a large wheel and you have to have two hands to turn it. And so each hand applies force, and there's, of course, a moment due to each of those forces. And the interesting thing about this is, the amount of torque required to turn the wheel is constant, regardless of where you place your hands. So put your hands a little closer together, you'll have to apply more force, but farther apart, it's easier. You probably already know that by intuition, or at least by your experience in everyday life. But we'll be able to actually calculate numerically what's going on and relate the forces to the couple generated by those forces. Here's another example. When you grip a steering wheel and you want to turn it, you push with one hand and pull with the other. And essentially you're applying a force couple to the wheel, which causes a torque about the rotation axis of the wheel, and therefore the wheel turns and you're able to steer. In this case, looks like he's driving a forklift or something, but you've probably experienced this in driving a car. Now, if you think about an older vehicle that doesn't have power steering, based on this, do you think that older car would need a larger steering wheel or a smaller one, and why? Think about that for a bit. Now, of course, there's other places along the steering mechanism where mechanical advantage can be introduced. But the steering wheel is one of those places. And so an older car that has no power steering, if you've ever driven one, they're extremely difficult to turn. And you need a larger wheel so that you could apply less force but have more torque in order to turn the wheels of the vehicle. So what do we mean by the moment of a couple? Well, it's defined as two parallel forces with the same magnitude but opposite direction that are separated by a perpendicular distance d. That's a mouthful, but you can see from the images what's meant by this. Now, the interesting thing about calculating the magnitude of the moment generated by this force couple is you actually don't need both forces. You just need the magnitude of one and the separation distance d, and then the magnitude of the moment is simply the force times distance. It's pretty simple, really. If you take the moment that way, what you're doing is summing moments about a point where one of the forces of the couple pass through that point, and therefore its moment arm is zero. And that's fine. There's nothing wrong with that. But another way to think about this, since we talk about wheels so often, is to sum moments about the pivot point of that wheel, about the center point. And then each force has half of the distance as the moment arm. Since the two forces are equal, you end up at the same place, where the moment about the pivot point is simply F times d. But it comes from two terms in that case. You can do that with scalar analysis. You can also take the cross product. So you can take an R cross F, where R is any position vector from the line of action of one force to the line of action of the other force. That will always work because the cross product takes care of any pieces that don't provide a torque or a moment. An interesting thing about a force couple like this is that the net effect of the force is just a couple. There's no force effect because the forces cancel out and all you end up with is a moment, which is the force times the separation distance, d. Now, since the moment of the couple depends only on the distance between the forces, the moment of a couple is a free vector. What that really means is that it can be moved on the body anywhere you like and have the exact same effect. And that's something that really confuses students because this is true in general of a moment. Moments can be applied at any point on a body that you like, assuming the body is rigid, and they will have the exact same effect regardless of where they are applied. Forces are not that way. The location of application of a force does affect the way that the body responds. One experiment you can try, if you ever, a lot of people don't work on their cars anymore, but if you ever have a car and you need to take the lug nut off and you forget, let's say you jack up the car and you put the wrench or the lug wrench on a lug and you start turning it, what you'll notice is the wheel starts turning. What's interesting is it really doesn't matter where you put your wrench. When you apply torque to that wrench, you will cause the same angular acceleration of the wheel as anywhere else. It doesn't matter if it's on the outside edge of the wheel or, well, I guess you can't really attach a lug wrench to the outside edge of a wheel, but if you could and apply the same torque that you apply to the lug nut, you get the same effect. You can get an adapter and attach the lug wrench to the there's always a nut on the front wheel. You have to often dig a little bit to access it because there's often grease caps and things. But anyway, you can access it and put your wrench there. And if you apply the same torque, the wheel will experience the exact same effect. And that confuses students quite a bit, that it doesn't matter where you apply a moment on a rigid body, it will always have the exact same effect. It's not like if you apply the moment to the body in one location, the body will spin about that point. Okay, not without other linear forces causing that point of the body to be held in place. But we're talking about just a pure moment. If you apply a pure moment to a body, you can apply it anywhere you want on the body and you'll have the same effect. So a force couple, regardless of where you apply it, the net effect of a force couple is a moment. And so by that logic, where you apply that force couple doesn't actually matter. You'll get the same effect on the body. Now, any moments made by a couple can be added together just like you would any other vector. Really, a moment is just a vector. That's all it is. And don't forget that the moment is represented as a vector in accordance with your thumb. So if you think about your right hand and the body rotating, or a moment being applied to the body, the direction of the moment is in the direction of your thumb. And that's how you indicate rotation with a moment, or a tendency for rotation, or an angular force, if you will.